In this module, we introduce the topic of electrolysis and Faraday's laws. Electrolysis is an important electrochemical technique widely used in industrial applications. It involves the application of direct electric current to drive non-spontaneous chemical reactions at the electrodes. Electrolysis is conducted within a specialized apparatus known as an electrolytic cell. This cell is comprised of two electrodes, the anode and the cathode, immersed in an electrically conductive liquid phase. The latter is commonly referred to as the electrolyte in this field. Another essential component of the electrolytic cell is an external power source. In certain configurations, a partition such as an ion exchange membrane or salt bridge may be employed. The function of this partition is to prevent the mixing of products formed at each electrode. The electrolyte contains free ions that can migrate under the influence of an electric field and carry electric current through the liquid phase. Besides its conductivity function, the electrolyte also serves as a reservoir of reactants for the electrochemical reactions occurring at the electrodes. To summarize, in an electrolytic cell, the electrolyte serves as the source of reactants and an ionic conductor of electric current. The electrodes act as the sites for the redox reactions, and the external power source provides the necessary electrical energy to drive the process. During electrolysis, the application of an external voltage to an electrolytic cell initiates various electrochemical processes. This voltage creates an electric field within the cell, prompting ions in the electrolyte to migrate towards the electrodes. This migration is governed by the charge of the ions. Positively charged cations move towards the negatively charged cathode, while anions bearing a negative charge are attracted to the positively charged anode. At the cathode, cations may receive electrons from the electrode and undergo reduction. This process involves the gain of electrons and may transform the cations into electrically neutral species. Conversely, at the anode, anions may donate electrons and undergo oxidation. This reaction involves the loss of electrons and may convert the anions into neutral species. The fundamental mechanism of oxidation and reduction in electrolysis is the transfer of electrons through the interface between the electrode and the electrolyte. The products of electrolysis often differ in physical state from the electrolyte, allowing for their separation and collection through various mechanical methods. For example, gases generated during electrolysis may be collected above the electrodes, while solid products may precipitate out of the electrolyte. The process of electrolysis was first quantitatively described by Michael Faraday, based on his electrochemical research published in 1833. The Faraday's law of electrolysis, quantitative relationships established based on this research, hold historical significance. They laid the foundation for understanding the relationship between the amount of electric charge used to drive an electrochemical reaction and chemical change, which means an amount or mass of a substance that was converted in this reaction. Faraday's first law of electrolysis states that the mass of a substance deposited or dissolved at an electrode is directly proportional to the total electric charge passed through the electrolyte. Faraday's second law of electrolysis further elaborates on this relationship by stating that when the same electric charge passes through an electrolyte, the amounts of different substances converted are proportional to their equivalent weights. The equivalent weight of a substance in this context is defined in modern terms as its molar mass divided by the valency number. The latter represents the number of electrons required to convert one molecule of the reactant. This law essentially links the amount of substance transformed during electrolysis to its chemical properties, particularly its molar mass and valency. In modern terms, Faraday's laws of electrolysis established a clear relationship between the electric charge and the chemical turnover during an electrolysis process. These laws can be understood through the fundamental concepts and constants of modern physics and chemistry. The number of electrons required to convert or discharge ions during electrolysis depends on their valency. A monovalent metal ion requires 1 electron for discharge and a divalent metal ion needs 2 electrons. This relationship could be less straightforward for more complex ions, as expressed by the valency of redox half reaction. If n electrons flow through the electrode-electrolyte interface, n over v molecules of reactant or product of interest are converted. The number of moles of a substance converted can be expressed as N over V times Na, where Na is Avogadro's constant. The total electric charge Q passed through the electrode-electrolyte interface is given by N times E, where E is the elementary charge. The mass m of the substance converted is related to the total charge by this equation. M equals capital M over V times F multiplied by Q. Here, capital M is the molar mass of the substance and F is the Faraday constant, which represents the charge associated with 1 mole of elementary charges. The value of F is approximately 96,485 coulomb per mole. According to this equation, for a given substance, when the molar mass and valency are constant, the mass of the substance converted is directly proportional to the total charge Q passed through the electrolyte. This is the statement of the Faraday's first law. On the other hand, for a constant charge, the mass of different substances converted is directly proportional to the ratio m over v. This ratio was named equivalent weight by Faraday, and this relationship was formulated as Faraday's second law. This modern interpretation of Faraday's laws provides a quantitative framework for understanding the electrochemical processes in electrolysis, linking the flow of electric charge to the chemical changes occurring at the electrodes.